Hello everyone, welcome to Brain Blitz Audios. In this episode of Mind Maps, we'll be dealing with the 11th chapter of the chemistry syllabus of grade 12 CBSE. It's known as alcohols, phenols, and ethers. We will be proceeding with this chapter with the help of a mind map. It is a very effective tool for last-minute revisions. However, mind maps can be pretty extensive. Therefore, we have divided this into 9 sections, which will help us to briefly explain each part in a simple and easy way. Let's begin, shall we? So, the first thing we're going to deal with in alcohols, phenols, and ethers is the classification of the 3 compounds. But before we start, let's look at what are alcohols, phenols, and ethers. So, an alcohol is a carbon compound that is OH at one end of the compound. And the compound is aliphatic. So that means it is a straight chain compound, compounds like these. Phenols also contain an OH ending, but they are aromatic compounds. So this is a phenol. What about ethers? Ethers are a special type of compound which contain the formula RO R-. So it is basically removing the hydrogen of the OH ending and replacing it with a carbon ending. So it becomes R0 R-. So that is the formula for an ether. These are sweet smelling compounds, and these are commonly used in association with alcohols and phenols. How do we classify alcohols, phenols, and ethers? In classification, we'll divide this into 2 parts. Alcohols and phenols are considered one type of compound because they have the same ending, OH, while phenols have this formula, RO R-. Alcohols and phenols are divided into 2 categories, into categories such as mono, di, tri, or polyhydric. So what do these mean? A mono alcohol would contain just one OH. Di will contain 2 OHs. Tri, 3, and poly means more than 3. So this is dependent on the number of OH endings in the carbon chain. These are also known as functional groups. Now, in the box, we get another type of classification, which is a classification regarding the carbon atom to which the functional group is attached. So the first case contains an OH attached to a carbon which has an sp3 hybridization, which means it contains only single bonds. Now these have the following arrangement: primary, secondary, and tertiary. In primary alcohols, it is connected with 4 bonds. These H2 would come into the structure respectively. So it has 4 bonds, which includes the bond with the functional group. In secondary alcohols, there are only 3 bonds for the carbon atom. That is 1 hydrogen, 1 functional group, and 1 linking to the rest of the chain. Tertiary means that the carbon atom has only 2 bonds, 1 with the main chain and 1 with the functional group. In this scenario, primary is considered more than secondary, which is considered more than tertiary. So this is in accordance with reactivity. The second type of carbon compounds, which are alcohols and phenols, contain the functional group attached to an sp2 hybridized carbon. Now these are atoms which have a double bond or a triple bond in them. And an example is vinylic alcohol. Vinylic alcohol is given as CH2CHOH. And it is also used for phenols. Phenols, since they have an aromatic compound, such as benzene, would have a partial double bond everywhere due to resonance. So it is contained in the second category, which is containing CsP2OH bond. So that means the functional group is attached to an sp2 carbon atom. Let's look at ethers. Ethers are simple. There are only two types of ethers. The first is simple or symmetrical. What this means is that the formula for the first kind would be ROR, which means the carbon component on both sides of the oxygen atom is the same. However, for a mixed or unsymmetrical ether, it will be ROR dash, where R dash is completely different from R. So in simple or symmetrical ethers, alkyl or aryl attached to O2 are same. And for mixed and unsymmetrical, two groups are different. So whether it's alkyl components or aryl components, ethers have only two types, that is simple and mixed. Let's move on to the nomenclature of alcohols, phenols, and ethers. The word nomenclature refers to naming a compound. So in chemistry, we have basically two systems of naming. One is common names, and the other is IUPAC names. Now, IUPAC stands for International Union for Pure and Applied Chemistry. For alcohols, the common name is alkyl group plus alcohol. So instead of all, it will be alcohol. It's AlCOHOL. So an example for this would be ethyl alcohol, which is C2H5OH. However, for the same compound, the IUPAC name would be gained by substituting the E of the alkane present in the compound with the suffix OL. So the alkane present here, C2, which means it's ethane, plus, and we remove the E and put an OL ending. So the IUPAC name would be ethanol, while the common name would be ethyl alcohol. So that is the simple system by which we find out the common name as well as the IUPAC name of alcohols. Let's move on to phenols. Common name. Terms such as ortho, meta, and para are used. In IUPAC names, the dihydroxy derivatives such as 1,2, 1,3, and 1,4 benzene-diol are used. Now, what does this mean? Now, suppose I have a phenol present here. This is the basic phenol, and it's the same for both the common name as well as the IUPAC name. Both names use the term phenol for the same component. So these positions are known as ortho. These positions are known as meta, and this position is known as para. So ortho, meta, para. So when we are having common names, if the second substituent is present here, we use ortho and then put the substituent's name. We use meta here. If the component is here, we use meta and then the substituent's name. And if the substituent is here, we use para and then the substituent's name. However, in the IUPAC name, we use the number 1 to denote the point where the functional group is attaching, and then we mark the others based on that reference. So 1, 2, 3, 4, 5, 6. So if it's ortho, it will be 2 or 6. Meta means 3 or 5, and para means 4. So dihydroxy derivatives in IUPAC naming are known as benzene diols. And if they are ortho, it's 1, 2. If it's meta, it's 1, 3. And if it's para, it's 1, 4. Let's look at ethers. Common name: alkyl or aryl groups in alphabetical order followed by ether. Now let's take a simple example. C2h5O CH3. So according to the common name, we will find out the alkyl groups present. So we have a methyl group 1C, ethyl group 2C, and since E is the first in the alphabet compared to M, we use the term ethyl, methyl, ether. So that's the common name for this compound. What about the IUPAC name? It says that in alkyl or aryl group, the E replaced by oxy, which is followed by the parent hydrocarbon. So this is known as the parent hydrocarbon, the one which is more. The one less is not the parent hydrocarbon, and it comes first. So the name for this ether, the IUPAC name, would be methoxyethane. So that is how. So these are the rules that you need to be careful about when dealing with nomenclature of alcohols, phenols, and ethers. Let's move on to the structures of functional groups. So it's pretty simple. So the functional group for alcohols and phenols is OH. Now this OH is attached to a carbon atom, which belongs to a chain, and it's attached by a sigma bond. So what happens is the S part of the sp3 orbital, which is a kind of hybrid orbital, which you've learned in class 11. So the oxygen and carbon sp3 orbital's S component overlaps. So that results in a sigma bond. So the reason why there's a sigma bond is it needs to be very strong, and alcohols generally are some strong components. So they have very strong bonds, especially where the C and the O meet. So that bond is a sigma bond, which is comparatively strong. Phenols also have the same perspective, but in that case, it will be an sp2 carbon atom. However, the difference comes in ethers. In ethers, there is a tetrahedral arrangement for 4 electron pairs. So basically, a tetrahedral shape is maintained by the electrons when both the alkyl groups attach to the oxygen atom. Let's move on to preparation. Now, according to your textbook, alcohols and phenols are first explained in their preparation, their properties, and some commercially important ones of alcohols and phenols, and then they move on to ether. So we'll be following the same rule. So let's look at preparation. Preparation of alcohols. Alcohols are formed by these 3 steps. The first step deals with from alkenes. So alcohols are primarily formed from alkanes. So alkenes are compounds with double bond, basically. And so there are two ways in which an alcohol is formed from an alkene. The first is acid catalyzed hydration, and the second is hydroboration oxidation. Now, in acid catalyzed hydration, the alkene present reacts with water, and since an acid is present as a catalyst, there'll be an abundance of H+ ions, and it forms an alcohol. Okay, so an alkene here reacts with water, and since acid is present as a catalyst, you have H+ ions in abundance, and then they form an alcohol of the same order. Now, the thing here is that suppose we have an unsymmetrical alkene, then this reaction takes place in accordance to Markovnikov principle, which in this principle, which states that the hydrogen part goes to the part of the alkene which has more hydrogen atoms, and the other part, which is the negative part, basically, it goes to the part where there's less, the part of the alkene or any compound which is under Markovnikov rule, which has less hydrogen atoms. So this Markovnikov principle is pretty important, because when you have unsymmetrical alkenes being acid catalyzed, we use this principle, and it's another principle from grade 11. So the second type of production of alcohols from alkenes is by hydroboration oxidation. Now, in this step, they use a substance known as diborane, which is BH3 twice. Okay, so what they do is they use this diborane to react with an alkene. So that's BH3 twice reacts with alkene to form trialkyl boranes. And this is the example given in your textbook. So this is an alkene here, and we have a diborane here. And then what we get, these are intermediaries which are already trialkyl boranes. So when they do this equation twice, so when they add the same alkene twice, they get a trialkyl compound here. So it's oxidized in the presence of hydrogen peroxide, which is H2O2, to give you an alcohol, which is present here. So diborane reacts with an alkene, and then consequently you add alkenes to the mix, and you get a trialkyl borane, which then gives you an alcohol. Let's go to the next type of reaction, which is from carbonyl compounds. There are two types of reaction in carbonyl compounds. First is the reduction of aldehydes and ketones. By here, the word reduction here means adding hydrogen. So you add hydrogen to an aldehyde or a ketone, you get an alcohol. The second way is by reduction of carboxylic acids and esters. Carboxylic acid is COOH, and esters is another special type of compound. So in aldehydes, reduction takes place in the presence of a catalyst such as palladium, and then they form an intermediate compound here, and then so then they form the alcohol. So this is for aldehydes. For ketones, they use NABH4 and then they form the alcohol. In reduction of carboxylic acids, we use H+, so it's taking place in an acidic environment, and then they use hydrogen gas as another catalyst to get their alcohol. The third type of equation, which is used to create alcohols, is from the Grignard reagent. So alcohols are produced by the reaction of Grignard reagents with aldehydes and ketones. So this is possible with aldehydes and with ketones. So it's a very complex reaction. So what in effect, you have the alkene. So you have the carbon compound, you have the Grignard reagent, which is MgX, and then you form an intermediate, which is very unstable, which immediately in the presence of water splits to give you the alcohol and another compound, which is a residue from Grignard reagent. Let's move on to the preparation of phenols. Phenols were isolated in the early 19th century, and now it's produced synthetically from many reactions. The first reaction is from haloarenes. So in this reaction, the compound here, which is chlorobenzene, is fused with NaOH. So it's fused with NaOH and then reacts at the following condition: 623 kelvins of temperature and 300 atmospheres of pressure to form a sodium phenoxide, which is ONA in the presence of OH, and then in the presence of HCl, which is known as acidification, we get phenols. The second equation, phenols can also be formed from benzene sulfonic acids. So benzene here is sulfonated with a compound known as oleum, and benzene sulfonic acid is formed here. Now, it is converted to sodium phenoxide using NaOH. And when you get a sodium phenoxide, it's further acidified with H+. So both of these reactions are clubbed up here. So then you get an alcohol, a phenol actually, which is an alcoholic functional group with an aromatic compound. Third, from diazonium salt. So aniline, which is NH2, which is benzene with NH2. Let me write it there. Aniline under the influence of nitrous acid. So nitrous acid is this compound here. So that's nitrous acid at 273 to 278 Kelvin forms a diazonium salt. This is a diazonium salt. And then they are hydrolyzed to phenols by warming with water. So you add water and you heat it, you get a phenol plus nitrogen plus HCl in this case. The last type of equation is from cumin. So phenols can also be synthesized from cumin. So what is cumin? This compound here is known as cumin. And so we oxidize it. So we add O2 and we get a compound known as cumin hydroperoxide. So this is the hydroperoxide part along with cumin. And then it is converted to phenol and acetone. So we know that this is phenol. So this is acetone. So it's converted with the presence of dilute acid. So what dilute acid means, you have H+, but you also have H2O in the mix. So the thing about this reaction is that the primary goal is to get phenols, but the byproduct, which is acetone, also is produced in large numbers from the reaction of cumin to get phenols. So it's a pretty useful reaction. So as we said before, we've now jumped into properties of alcohols. Now this section contains both alcohols and phenols. Let's look at physical properties. The first property states that boiling point increases with increase in the number of C atoms. What does this say? The longer the carbon chain, the higher the boiling point. So if you have a short carbon chain attached to an OH functional group, it has a lower boiling point in comparison with a longer carbon chain attached to the OH functional group. The second point states that solubility decreases with increase in size of alkyl or aryl groups. So when we increase the size of alkyl or aryl groups, which basically means increasing the chain or the ring compound that is part of the OH functional group, the solubility in a solute decreases. So the shorter the compound, the greater the solubility. Let's look at chemical reactions of alcohols. By the way, the physical properties are common. So both alcohols and phenols have the same physical properties. It's in the chemical properties that they vary. So chemical reactions. Alcohols are versatile compounds. So that means they have a lot of chemical reactions in their way. They react both as nucleophiles, which is electron taking, and electrophiles, which means electron giving. The bond between OH is broken when alcohols react as nucleophiles. So ROH plus C implies that this bond will be broken. So it becomes ROC plus H plus. So it's not just when alcohols are nucleophilic that this bond is broken. When they're electrophilic as well, it is also broken. So based on the cleavage of OH and CO compounds, so this breaking of the OH bond, the bond between O and H, is known as cleavage. And so based on this cleavage property, the reactions of alcohols and phenols may be divided into two groups. So the first would be reaction with metals. Alcohols and phenols react with active metals such as sodium, potassium, and aluminium to yield corresponding alkoxides or phenoxides and hydrogen. So the first equation here, 2ROH, an alcohol, plus 2Na, Na is a metal, gives you the alkoxide, RONA, plus H2. So this is the most simple example of a reaction of an alcohol with a metal. So the acidity of alcohols is in this order. Primary alcohols are more acidic than secondary alcohols, which are more acidic than tertiary alcohols. In phenols, AR, which is the aromatic part, plus a carboxylic acid gives you an ether, yes, it's an ether, plus H2O. and ROH, which is an alcohol, plus HX, which is a haloalkane, gives you an alkyl halide plus water. So we have an alkaline component, such as HCl or HBr, and then we have an alcohol here, so we get an alkyl halide and hydrogen. I mean, not hydrogen, water, which is H2O. Another reaction given is C2h5OH, which is ethanol, present in H2SO4 at the temperature of 443 degrees Kelvin, giving you an alkene, which is of the same order, plus water. So this is another alcohol, which when oxidized, gives you a compound with a coordinate bond. So these are the various reactions present in alcohols. Let's look at phenols. Phenols in the presence of dilute HNO3 will form hydroxynitrobenzene compounds, which are both ortho and para. So the phenol forms a bond with an NO2 compound in the ortho position and the para position. In concentrated HNO3, so in concentrated HNO3, what happens is that both the ortho and the para positions of phenol are occupied by the NO2 substituent. Let's look at the next reaction. Phenol in the presence of a halogen, which is bromine, in CS2, which is carbon with 2 sulfur, at the temperature 273 degrees Kelvin, would give you a phenol with a halogen, both in the ortho position and the para position. The reason why most of them are ortho and para is that the OH functional group is an ortho and para directing group. So what it does is when a new component comes as a substituent, it guides them to the ortho and para positions for maximum stability. Phenols in an excess of halogen would form a compound which has a halogen in both the ortho and the para positions. Let's look at the next reaction. Phenol in the presence of Zn changes to benzene, which is the ring without the OH, plus ZnO. So basically, it reduces to benzene. And finally, phenol in the presence of Na2Cr2O7, which is sodium permanganate, in the presence of H2SO4, which is sulfuric acid, gives you this compound. Now, we have 2 reactions present below, which are pretty important. So let's look at each of these reactions. They're known as Kolb's reaction and Riemann-Tiemann reaction. What is Kolb's reaction and Riemann-Tiemann reaction? In Kolb's reaction, the phenol in the presence of NaOH changes to sodium phenoxide, which in the presence of carbon dioxide gas and acidic compounds such as HCl, which means there's an increase in H+ ions, would change to a orthohydrobenzoic acid. So this compound here is known as orthohydrobenzoic acid. That means the acidic group, which is COOH, now becomes the functional group. So, and it's present in the ortho position since OH is an orthodirecting and paradirecting compound. So it becomes orthohydroxybenzoic acid. This is the main reaction product of Kolb's reaction. So phenoxide ion generated by treating phenol with sodium hydroxide is even more reactive than phenol towards electrophilic aromatic substitution. So it undergoes electrophilic substitution with carbon dioxide, which is again a weak electrophile, in an acidic environment to give you orthohydroxybenzoic acid. This is the first reaction. So the product here is known as 2-hydroxybenzoic acid, specifically, which is also known as salicylic acid. Again, an important acid used in the production of aspirin, a drug. Let's look at Riemann-Tiemann reaction. In Riemann-Tiemann reaction, the phenol reacts with chloroform and aqueous sodium hydroxide to give this compound. It's a phenoxide compound, but also contains a CHCl2 component. So on treating phenol with chloroform in the presence of sodium hydroxide, a CHO group is introduced at the ortho position of the benzene ring. So this is the CHO group. So from here, if we progress the reaction with NaOH, we get a CHO group here in the phenoxide derived from phenol. So CHO means that this compound becomes an aldehyde. So basically, you're converting a phenol into a hydroxyaldehyde. Again, the name of this particular compound is known as salicylic aldehyde, which again is pretty important in producing aspirin. Now let's look at the commercially important alcohols present. The first is methanol. Methanol is CH3OH. It is very important because it's used as a solvent in paint, which is what we cover our articles with. Varnishes, which is used as building material, and making a compound known as formaldehyde. It is also known as wood spirit because originally it was found by destructive distillation of wood. Most of the methanol today is produced by catalytic hydrogenation of carbon monoxide at high pressure and temperature and in the presence of ZNO Cr2O3 catalyst. It is a colorless liquid and boils at 337 degrees Kelvin. It's also highly poisonous. Let's look at the next component, which is pretty important as alcohol in the industries, and it is ethanol, C2h5OH. This is the alcohol used in drinks. So it's obtained commercially by fermentation. The oldest method is from sugars, and the sugars are contained in molasses, sugarcane, grapes, etc. Let's look at the functions of it. Ethanol is used as a solvent in the paint industry, and it's also used in preparation of a number of carbon compounds, with addition to its role as the primary component in drinks, such as wine. Let's move on to ethers. How do we prepare ethers? The first thing is by dehydration of alcohols. So we have an alcohol here, and we expose it to sulfuric acid at a temperature of 413 degrees Kelvin to form an ether. So let's try to name it. So this is ethanol. Remember our earlier part about it being used to create other carbon compounds present in H2SO4 at 413 degrees Kelvin to form C2H5O C2H5, which is ethoxyethane. The second reaction is a named reaction, and it's known as Williamson's ether synthesis. So in here, an alkyl halide reacts with a sodium alkoxide. So this is alkane, and this is an ONA part of it. So it becomes a sodium alkoxide, and this is an alkyl halide, which changes to become ROR dash, which is the general formula for ethers, and then it turns into, the remaining part turns into sodium halides. So phenols plus NaOH gives you sodium phenoxide, which when taken under alkyl halides gives you benzene with an OR component as its functional group. Let's look at the physical and chemical properties of ethers. First property, the CO bonds are polar, which means to say that in an ROR dash component, if these bonds are cut, then this will gain a positive charge and it will gain a double negative charge. That is the meaning by breaking polar bonds, because polar bonds are when electron transfer occurs. Boiling points of ethers are comparable to those of alkanes. So if we have CH2O, CH2, the boiling point of this would be comparable to C2H6. That's the meaning behind boiling points being comparable to those of alkenes. The third property is that these compounds, ethers, are soluble in H2O. It's pretty important because most carbon compounds are not soluble in H2O. They are more soluble in alcohols. Now, ethers are special because they are soluble in both alcohols and water. The reason being, ethers have polar bonds with them, and they also have huge alkyl groups which contain those polar bonds. So it can both be soluble in water as well as in alcohols. Let's look at chemical properties of ethers. So the first thing that happens is that the carbon-oxygen bond always gets cleaved. It means it gets broken. So it takes place in drastic conditions with an excess of hydrogen halides, these components. So the reaction of dialkyl ether gives two alkyl halide molecules. So the basic reaction would be ROR plus HX gives RX plus ROH, and ROH plus HX gives you RX plus H2O. That is the complete dissociation of an ether. So let's look at a reaction here. We have an ether known as benzyl methyl ether. So this component is divided into two reactions. The first reaction is the excess of bromine in ethnic acid. It gives an ether which contains a bromine atom in it. so it changes to another compound. So it is both present in ortho and para positioned bromine atoms, and one of them is the major product. The major product here is para. So it's this group that is more found in this reaction. So this is the major product, the part where bromine is present in the para position. It's known as para-bromoanisole, and the other component is known as O-bromoanisole. So when an ether contains a halogen, it's known as anisole. Okay, and in the second reaction, the ether in the presence of H2SO4 and HNO3, which are concentrated, yields these components. So what happens is nitration occurs. In nitration, anisole reacts with a mixture of concentrated sulfuric and nitric acids to deal a mixture of ortho and para nitroanisole. So ether with this group is known as nitroanisole. And yet again, we have both ortho nitroanisole and para nitroanisole. And over here, the para nitroanisole is again the major product, so it's found in more quantity. Let's look at another named reaction, which is pretty important, and it's known as Friedel-Crafts reaction. In Friedel-Crafts reaction, we take an alkyl halide and react it with an ether in the presence of anhydrous AlCl3 to form compounds. These compounds are known as toluenes. So the reason why they're known as toluenes is that the methyl group gets attached to it. So it becomes a toluene, which is benzene plus a methyl group substituent. So there are two types of Friedel-Crafts reaction. This is alkylation. Okay, let's write it down. There are two types, alkylation and acylation. Now this has to do with whether there is an alkyl group or an acyl group present here. So this is an alkyl group, while this is an acyl group. Okay, so this is alkylation and this is acylation. So in alkylation, they form methoxytoluenes, and since it's present in ortho position, this becomes 2-methoxytoluene, and this becomes 4-methoxytoluene because it's in para position, and the compound in the para position is again the major product. And when we have an acylation reaction, which is present under Friedel-Crafts reaction, we take the compound plus CH3COCl in the presence of anhydrous AlCl3, which is very important reagent. It's always used in Friedel-Crafts reactions, whether alkylation or acylation, to form acetophenols. Now this is methane, so we call it 2-methoxyacetophenol. And this, because it's in the second position, it's in the ortho position, and this is 4 because it's in the para position. And again, the one in the para position is the major product. And so that, in short, completes the chapter, alcohols, phenols, and ethers. Did you know that Blitz Audios specializes in providing free educational content to all? To be a part of our journey, please subscribe to this channel. Thank you for watching the video. We'll be back with more mind maps and other educational content. See you soon. Bye-bye.